In the early 1800s, steam power ran the modern world. It drove factory machines, pumped water from mines, and pulled heavy loads where muscle and wind fell short. Steam did one thing extremely well. It turned heat into steady force. But it came with a price. A steam engine needed a boiler, water, fuel, and constant attention. Power existed, but it was tied to bulk. That bulk shaped everything. In a factory, weight did not matter much because the engine stayed put and belts carried motion across the building. On canals and railways, steam made sense because a large vehicle could carry its own machinery. Yet people wanted smaller machines that moved independently. That was where steam struggled. It started slowly, warmed up reluctantly, and demanded space for its plumbing. Steam also punished anyone who needed quick, flexible power. A farmer, a small workshop, a delivery cart, none of them could wait while pressure built or haul a boiler just to do a short job. The engine that had transformed industry still felt wrong for everyday movement. The problem was clear and stubborn. The world needed power that travelled lightly, started fast, and fit inside a compact machine. Inventors started asking a blunt question. What if the fire happened inside the machine, not under it? Instead of boiling water and waiting for pressure to build, they tried trapping a fuel and air mixture in a cylinder and igniting it on purpose. The idea sounded reckless, but it promised something steam struggled to deliver. Power that came fast from a smaller package and could be aimed at motion directly. Early experiments used manufactured gas, the same kind made for lighting streets and homes. Engineers built gas engines that pulled in the gas, sparked it, and used the expanding hot gases to push a piston. That piston turned a crank, and the crank produced rotary power. It worked. That mattered more than elegance. Controlled explosions stopped being a theory and became a mechanical fact, measurable at a spinning shaft. But the first machines disappointed as often as they impressed. Ignition misfired, mixtures varied, and parts overheated or broke under sudden pressure. They drank fuel, produced uneven power, and demanded constant attention. No one could yet trust them the way factories trusted steam. Still, the direction was set. If an engine could survive repeated bursts of combustion and keep turning, then mobility no longer required a boiler at all. The big obstacle still remained simple. An engine had to fire again and again without tearing itself apart and without wasting most of its fuel. Then a clearer idea arrived. It treated combustion not as a single violent push, but as a repeating routine. Air and fuel went in. The mixture got squeezed. It fired. The exhaust got pushed out. 4 distinct steps in a fixed order turned chaos into a schedule. In 1876, Nikolaus Otto built an engine around that sequence, and it changed what people expected an internal combustion machine could do. The key moment came before the flame: compression. By squeezing the mixture first, the burn became faster and stronger, and the same amount of fuel delivered more useful work. Suddenly, the engine did not have to be enormous to be powerful. It just had to be disciplined. This 4-stroke cycle also solved a practical problem engineers kept tripping over: timing. Each stroke gave a clear job, and that made valves, ignition, and moving parts easier to coordinate. It ran smoother, it ran more predictably, and because it repeated the same controlled pattern, it offered a path to better efficiency instead of constant improvisation. From here, compact engines no longer sounded like wishful thinking. They sounded like engineering. The next leap did not come from a new cycle. It came from a new fuel. Early gas engines often depended on a fixed supply of manufactured gas, tied to pipes and storage. That kept power close to the workshop. Then inventors turned to gasoline, a liquid that could be carried, poured and stored in a small tank. Suddenly, an engine no longer needed a gasworks nearby, it only needed fuel on hand. In the 1870s and 1880s, engineers such as Nikolaus Otto and Gottlieb Daimler pushed that idea into real products. Gasoline had to become an ignitable mist, not a puddle, so mixing air and fuel became a practical craft. Ignition mattered just as much. Hot tubes and other awkward methods gave way to timed electrical sparks that arrived when the piston needed them. Reliable timing turned occasional bursts into steady rotation. That combination changed what an engine could be. A liquid fuel tank replaced bulky gas holders. A spark system replaced uncertain flame tricks. And because gasoline carried its energy in a compact form, the whole machine shrank while its usefulness grew. Power started to travel. It could sit on a small frame, move between jobs, and follow people instead of forcing people to come to it. Portable power stopped being a dream and became equipment. Once gasoline engines became portable, a new question appeared fast. Could that power actually carry people every day? Early motor carriages had proved the idea, but they broke down, overheated, and behaved differently on every trip. The engine did not just need to run, it needed to start easily, respond smoothly, and keep running when the road turned rough. Otherwise, the automobile stayed a stunt. The biggest battle happened at the fuel-air mix. Carburetors had to deliver gasoline in a steady, predictable way, not as a lucky accident. Too rich, and engines fouled and wasted fuel. Too lean, and they stumbled or stopped. At the same time, heat became an enemy that could not be ignored. Better water jackets, radiators and pumps kept temperatures under control long enough for real travel. Then the power had to reach the wheels without destroying itself. Clutches, gearboxes, chains and drive shafts all demanded tougher materials and smarter layouts, so torque did not snap parts or shake the machine apart. Makers refined these systems through constant failures, then quieter successes. Gradually, the car stopped feeling like an experiment. It started acting like a product, one that could be trusted to move, stop, and move again. At first, gasoline cars stayed expensive because they stayed handmade. Parts varied from one vehicle to the next, so repairs took time, and building a new car took even longer. Then a different idea took control. Build the same car the same way, again and again. Standardized parts meant a wheel hub, a piston, or a gear fit without custom work. That change sounded small. It reshaped everything. Mass production pushed that logic to its limit. Instead of one team assembling one whole car, the work broke into repeatable steps, and cars rolled forward as each step finished. Output rose fast, and costs dropped with it. Factories bought materials in bulk, tools lasted longer, and workers repeated one task until it became quick and predictable. The result mattered more than speed. Millions finally afforded a car. Affordability changed transportation at the scale of daily life. Railroads still moved crowds and freight, but they ran on fixed routes and fixed timetables. A personal car answered to one person's needs, not a station clock. Travel shifted from planned trips to casual trips, from shared schedules to private decisions. Roads mattered more, suburbs spread farther, and businesses followed the new freedom. Mobility became on demand. Gasoline engines changed everyday travel, but a hard limit remained. When loads grew heavy and runs grew long, gasoline wasted too much fuel and asked too much from its parts. Then a new idea arrived with a different kind of fire. The diesel engine used compression instead of a spark. Air got squeezed until it heated up, and fuel ignited the moment it entered. Simpler in one way, tougher in another. That squeeze did more than start combustion. It pulled more work from each drop of fuel. Higher compression meant higher efficiency, so the engine turned fuel into motion with less waste heat. The trade-off was weight and strength. Diesel parts had to survive extreme pressures, so the engines ran slower and heavier. But for the jobs that mattered, that was an advantage. They delivered steady pulling power, hour after hour. With that efficiency, new doors opened fast. Trucks carried more freight farther without constant refueling. Ships gained a practical engine that suited long voyages and massive propellers, reducing costs that gasoline could not touch. In factories and remote sites, diesels ran pumps, generators, and heavy machines reliably, using fuels that stored and handled well. Gasoline still ruled the small and quick. Diesel claimed the world of weight, distance, and duty. In the early 1900s, the internal combustion engine stopped being just a tool for business and travel. It became a tool of the state. Armies that once depended on horses and rail timetables started betting on motor transport. Trucks carried food, ammunition, and spare parts where tracks did not reach. That simple change stretched a battlefield outward. Movement no longer followed rails. It followed fuel. Once engines proved they could move heavy loads, militaries pushed them into fighting machines. Tanks appeared as armoured vehicles that crossed broken ground and helped break trench lines. Their power came from the same idea as a car, scaled up and hardened for war. But tanks alone did not win campaigns. They demanded constant repair, constant fuel, and constant resupply. The engine created a new weakness. Air power amplified that demand. Aircraft relied on internal combustion engines, but they also relied on everything behind the runway. Fuel trucks, generators, compressors, and transport to move bombs and parts. War turned into an enormous logistics problem, and engines sat at the center of it. By mid-century, strategy depended on keeping vehicles running. Control of oil, roads, and supply lines decided what armies could do. By the late 20th century, the engine faced a new kind of enemy, its own exhaust. Cities choked, smog warnings rose, and governments responded with hard rules on pollutants and fuel use. For car makers, this meant old tuning tricks no longer worked. Power could not simply be poured out of the tailpipe. The engine had to change in a way drivers barely noticed, yet the air did. The catalytic converter became the turning point. It sat in the exhaust stream and used heat and chemistry to turn toxic gases into far less harmful ones. But it demanded cleaner fuel and tighter control. Carburetors, with their crude guesswork, started to lose. Fuel injection took over, measuring and delivering fuel with precision. Sensors watched oxygen in the exhaust, and the mixture adjusted constantly. Waste dropped, drivability improved. Then computers moved from optional to essential. Engine management systems coordinated spark timing, fuel, idle speed, and emissions hardware as one plan, thousands of decisions per minute. Turbocharging returned in a new role, not just for speed, but for efficiency, using exhaust energy to push more air in so smaller engines did bigger jobs. The result looked familiar from outside. Inside, it became a cleaner, optimized machine. By the time the world reached the present, the internal combustion engine still did most of the daily work. It moved people to jobs and schools. It hauled food, fuel, and building materials. It powered delivery vans, farm machines, buses, ships, and much of long-distance trucking. Steam once ruled because nothing else could. Combustion replaced it because it fit inside the vehicle and started on demand. That success built a new kind of society. Roads expanded because cars and trucks needed them. Cities spread outward because commuting became normal. Supply chains stretched across continents because diesel freight ran day and night. Everything assumed cheap liquid fuel, fast refueling, and engines that survived years of vibration and heat. The machine did not just serve the modern world, it shaped how the modern world worked. But the same design that made mobility easy also produced a growing problem. Burning fuel released carbon dioxide, and the scale became impossible to ignore. Governments tightened rules, buyers demanded lower costs to run, and new electric drivetrains improved quickly. Combustion still carried much of the planet, yet it faced pressure from batteries, charging networks, and climate targets. Steam had once seemed permanent too, until a better fit arrived.